We continue with our discussion on application of diffusion theory, or mass transfer theory rather, because diffusion we have addressed yesterday. Yesterday, if you remember, I have talked about a solid state carbonization process, gas carbonization process, nitriding process, given you a little bit idea about the diffusion processes which one would encounter in the context of galvanizing, for example, and in that context also I have told you that diffusion with reaction, how the equations get coupled, etc. So I think that sets the background for tackling of diffusion related problems based on the fundamentals that we have learned. And now I want to discuss today a convective mass transfer problem which is of great significance, and this is the problem of alloying. And you all know that alloying is a very important process, and basically what we would like to do here is a solid liquid mass transfer. That is the phenomena that is so I'll describe a little bit about alloying first, and then we'll see whatever we have learned in the context of solid liquid mass transfer, how those knowledge can be applied to investigate alloying. And also, once I discuss this solid liquid mass transfer problem, I would also like to introduce a special topic on also which is very applied in nature, that is the reduction of iron ore or iron oxide with carbon monoxide, and where I intend to show you that I may not consider the kinetic steps to be at equilibrium and then consider the resistance is not just made up of one single step, but several steps which are working in series. So these are the two problems that I wish to discuss today. So let us start with the process of alloying. Alloying, as you all know, is very common in metallurgy. Okay, steel, for example, is an alloy, and you see aluminum alloys extensively used, titanium alloys also extensively used. Aluminum alloys, for example, in aerospace industries, in light material applications. Steel, of course, you know that most of the nuclear reactors and many other stuff, they are made out of alloy steels, and there are actually many special or alloy steel plants. That is their regular business. So in transportation sector, in health sector, in the nuclear energy sector, alloy steel finds extensive application. So what is the procedure for alloying of steel? Basically, the alloying is a procedure of addition of solids in the requisite amount. Suppose you want to make tungsten steel. Tungsten steel, you must all be knowing that this is the one grade of tungsten steel is the tool steel, which is used as the cutting tool in lathe machines, to which you are already exposed to. And that's so if you want to make tungsten steel, basically what is done is in liquid steel, which does not contain much of oxygen or which is killed, and then under that condition, we add alloying elements so that the alloying elements can dissolve into steel. Now, certain alloying elements will melt in steel, and I have already given you that basic background. When the melting point of the alloying addition is smaller than the bulk liquid temperature, then the melting phenomena is going to be encountered. And when the melting temperature of the addition is higher than the bulk temperature, in that case there is no melting involved, there is dissolution which is involved. And in that context, if you remember, I said sugar does not melt in water, sugar dissolves in water. Similarly, if you want to make from a low carbon to a high carbon steel, okay, so the carbon will not melt in steel because carbon's melting point is far greater than the operating temperature of liquid steel, and carbon basically dissolves. So similarly, tungsten also, tungsten's melting point is very high, much greater than 2500 degrees centigrade, higher than that. So it will not melt in steel at 1600 degrees centigrade, tungsten will dissolve in steel. So basically, we are talking about now solid liquid. So it is basically, we can consider it to be predominantly occurring at isothermal conditions. So it is not the melting phenomena that we wish to investigate, but we want to investigate dissolution. But as I said, that alloying may involve, because for example, if you want to make chromium alloy steel, chromium will melt in steel. Okay, first melt and then dissolve into steel. But so that is a two liquid mass transfer process. And here what we are going to do is from solid the mass transfer is taking place via the dissolution process. So, this is the only reaction that if you have a solid X and that solid gets dissolved into the liquid. Okay? So, there is no melting involved. So, bulk alloys are produced by adding solid liquids, solid materials or solid alloying elements to liquid steel, and there what happens is that the solid progressively dissolves in liquid, giving rise to the desired final composition. And as you all know that the more, if you add sugar, you have to stir it to dissolve. So, all the alloying process will involve that there is good amount of stirring, because the stirring is going to aid the dissolution process that we have seen, because stirring will influence the velocity field, and the velocity field will in turn influence the effective concentration boundary layer, which is just adjacent to the solid interface. Okay? So, that I have already explained to you. So, this is, if this is the solid surface and this is the concentration profile, and we know that the slope of the line gives us the effective concentration boundary layer thickness, and this distance, okay, this is the concentration and this is the distance, and this is x is equal to 0, and this distance, which is delta SAD effective, it is a function of the velocity, and more is the velocity, higher is the rate of dissolution. That is why the sugar will never dissolve in a cup of tea unless you stir your tea with a spoon or a stirrer. So, all the mass transfer operations or alloying operations will be done under reducing environment. We do not want the alloying elements to react with the environment and become oxidized. We want the alloying elements to go inside steel or inside aluminum or inside any other metal, okay? And therefore, it will be done under reducing atmosphere when the metal does not as such contain much of the dissolved oxygen, and it will be done under the condition of a stirring, and that will be obvious for us. So, if you have a solid, so this is the chemical reaction that will take place at the surface. So, the solid is going to, if you have added, for example, a spherical solid, shaped solid into a liquid. Okay? So, at the surface, which is the interface, at this interface, that reaction, so this is the capital X, we will have the chemical reaction taking place, and once the reaction occurs, then we have the boundary layer adjacent to, and then the transport takes place through the boundary layer, and then of course from the edge of the boundary layer the material. So, the reaction takes place, then the first transport takes place through the boundary layer, and then the bulk transport takes place, and this is the concentration profile. In the bulk, we are assuming there is good amount of stirring. So, most of the dissolution processes are dealt as a boundary layer mass transfer controlled phenomena, where there is no melting involved. Okay? So, this is from solid straight away to the dissolved without an intermediate liquid phase, like tungsten, niobium, carbon and steel, for example. Similarly, if you say aluminum silicon, silicon's melting point is greater than aluminum's melting point, so silicon will dissolve in aluminum. Okay? So, there, if this is silicon and this is liquid aluminum, then you will see this kind of a reaction taking place at the interface. And once the reaction takes place, and then we have the second step is the transport across the boundary layer, and third is from the edge of the boundary layer to the bulk. Of the three steps, it is assumed that this reaction is taking place at equilibrium, okay? And this transport from the edge of the boundary layer to the bulk is also very rapid because of the fact that we have a high velocity component. It is only adjacent to the solid surface that the velocity magnitude is going to be smaller. So, the resistance is going to be appreciable here, but the resistance is not really appreciable in the bulk of the liquid. So, step 1 and step 3 are going to be ignored. So, the entire rate of dissolution will be assumed to be controlled by the rate of transport of X across the boundary layer, and therefore, we have this equation that applies. We will write small km, the mass transfer coefficient, and this is the surface concentration, and minus this is the bulk concentration. Typically, what you would see that this surface concentration is as in accordance with this particular chemical equilibrium of this particular chemical reaction. Okay, if you write the equilibrium constant, then this is the dissolved concentration on the liquid side, and this is the solid concentration. So it's a pure solid, the activity is equal to 1, and this concentration actually is the saturation concentration, because that is the equilibrium concentration. Okay? Now, saturation concentration in equilibrium with the pure solid X, and because sugar, if you start dissolving sugar, at one point what is going to happen, that sugar will saturate the solution and no further dissolution, no matter how hard you can stir the cup, okay, or the liquid in the cup, no further sugar dissolution will take place, and in that case the concentration of sugar in the liquid phase is exactly equal to the concentration of sugar in the solid, which essentially means that the solid liquid has reached its saturation concentration point, and therefore no further dissolution is possible. So if this reaction is assumed to be equilibrium, then logically this concentration has to be the saturation concentration limit, and therefore this concentration is known a priori if you know the composition of liquid, if you know the temperature, and therefore, for example, if you tell me that what is the sugar saturation concentration of sugar in water at room temperature, which we call as solubility, this can be found out in standard books, chemical engineering handbooks, and so on and so forth. So for different alloying elements this can be. Now this saturation concentration is typically much larger than the bulk concentration in most of the cases, because alloying steel, if you make alloy steels, we say carbon is 0.8%, 0.7%. If you make tungsten, maybe 4% or 6% tungsten. So most of the time these saturation concentrations are much larger than the bulk concentration. Okay, it is only in some high alloy steels this value could be comparable, and this is therefore either you can take it to be almost negligible in comparison to CS, or if you want to take it CB, okay, in that case the CB is to be taken as a function of time, because as dissolution is taking place, the bulk concentration is progressively changing as a function of. So there are two separate class of problems. In one case, case 1, where we have the bulk concentration is negligible, that means we are talking of dilute solutions 1%, 1.5%, 2%, and so on, 2% X in liquid, and the saturation concentration could be appreciated very relatively much higher. For example, you say if you take the saturation concentration of niobium or tungsten in steel, they are of the order of 3000 kg per meter cube. On the other hand, and that 3000 kg per, you can have at the most tens of kg of meter cube, that is the concentration of those alloying elements in the bulk. So in the vast majority of the cases, one can, as a first approximation, consider this to be approximately is equal to 0. Now this is n dot, the rate of transport, because this is area, and this, if you consider a spherical shape, in that case this can be given in terms of dr over dt, in which r is the radius, and this will be given in terms of km cs star multiplied by rho s, where rho s represents the density of the solid, which is represented as x. Okay, so if you do a mass balance, then that's what rate of transport, that rate of change of mass. So if you have 4/3 pi r cube is mass at one instant, and 4/3 pi r minus delta r cube is mass at another instant, and then that much amount of mass reduction of the sphere is exactly equal to the right hand side, and you will be able to get this expression through mass balance itself. And this area here and the differentiation will cancel out that 4 pi r square factor, and therefore you are going to get this final expression under the condition that the bulk concentration is taken to be is equal to 0. So therefore the complete dissolution time, so this is at r is equal to r0 is the initial radius and t is equal to t0, that is the condition. So complete melting dissolution time, okay, can be calculated that once you integrate this equation and you set that my final r is going to be is equal to 0. Okay, if initial r is there, so if you integrate this term from r0 to 0, okay, so you take the dt on this side, so therefore we can say this can be taken, and therefore dt, and this corresponds to r0 when time is equal to t, and this is the 0 when there is going to be TCM, complete melting time, and if you integrate this. But you will require the value of Km. Cs star, as I said, is known to us, rho solid is known to us, so therefore the value of Km, the mass transfer coefficient, will be needed. Now, the mass transfer coefficient, as you all know, because it's a spherical geometry, so we can, if the flow is laminar, in that place we can apply diameter based Reynolds number and Schmidt number raised to the power 1 by 3, the Range-Marshall rule. And if the intensity of flow is very large, in that case, this time the Sherwood's number value will be something like 200, 300 or 400, okay? And in that context the value of 2 could be ignored. So it is 2 is very important parameter when the intensity of the flow, when the right, this term, the contribution of this term is of the same order. But if the contribution of this term, when Schmidt number is large, for example 500 or so, Reynolds number is also large, in that case the contribution of this term could be much higher than 2, and therefore the Sherwood's number can be approximated. And if the flow is also turbulent in nature, in that case one can write down intensity of turbulence, for the values of m and n are known and given in the literature if one finds out. So this will allow, this gives us a framework, because Sherwood's number is equal to mass transfer coefficient divided into characteristic length, which is the diameter, divided by the diffusion coefficient. So therefore the Range-Marshall correlation, or the limiting form of the correlations that I have represented, one for turbulent flow and one for relatively high Reynolds number, or relatively when the dissolution process is dominated by this term rather than 2, one can apply either of these equations and then one can calculate the Sherwood's number, from which one can find out what is the mass transfer coefficient. But note that if you do this exercise, then obviously the Km will come out to be a function of diameter. For example, you can imagine that if you take, for example, this correlation, then you will see that the Km will come out to be proportional to d to the power half, and then it is here is proportional to particle diameter raised to the power minus half, where half comes from, it's a characteristic length in the Reynolds number is d to the power half, and then there is a d in the numerator on the left hand side. So the mass transfer coefficient, if all other parameters remains constant, will come out to be. So there is a dependence of mass transfer coefficient. If you put the value of d as the initial diameter, in that case what you can at best get is the rate of dissolution dr over dt, as I have written about, minus dr over dt, which we call as the rate of dissolution of the spherical object, which is equal to mass transfer coefficient into this divided by rho s. And if you apply a Km value which is constant, and that Km value is deduced on the basis of initial diameter of the sphere, in that case the dr over dt that you are going to calculate will only represent the initial rate of dissolution. You must understand that if I put the diameter versus time, okay, in accordance and use a constant diameter, I will then Km, nothing changes there, steady state studying process. So the Reynolds number will be constant, this is already constant and this is already constant. So if I assume that I want to perform the calculation considering the initial radius or initial diameter of the sphere, then obviously this right hand side being a constant, you are going to get a straight line variation between d or r versus t. Instantaneous radius or diameter will change as a function of time in a linear way, but actual graph is going to be not linear because of the simple fact that Km is not constant, but it is changing as the diameter is changing, okay? And as the smaller diameter becomes smaller and smaller, okay, the mass transfer rates become higher and mass transfer coefficient becomes higher and higher. You can analyze this problem. For example, in cupboards, when you put mothballs, okay, initially the mothball really shrinks very rapidly, but the last trace, when it becomes very, very small, it does not really evaporate, or the mothball seems to be maintaining its size, particularly when the diameter is small. But we see here that as diameter is getting smaller, the mass transfer coefficient should get larger, but that is a scenario. Initial reduction, initially what happens within the cupboard itself, there is no naphthalene vapor, the bulk concentration is equal to 0. So, the driving force for mass transfer is extremely large. On the other hand, after some time the diameter has rapidly decreased to a smaller size, but then what happens, even though the mass transfer coefficient becomes larger at that case because the diameter is smaller, what happens, the cupboard becomes filled with naphthalene vapor, and as a result of which the driving force for mass transfer, it becomes very slow. So, that is why the last traces, the tiny naphthalene balls appear to remain in your cupboard forever, because the enclosure in which you have kept the naphthalene ball becomes almost filled with naphthalene vapor, causing the driving force C S star minus C B. And in that case, what is happening? Naphthalene is getting evaporated. So, it is a problem associated with, I would say, looked at from the same standpoint, it is a diffusion process, but nonetheless it is an analogous scenario as it is considered in this particular problem itself. You can consider air to be a fluid phase, and this naphthalene vapor, of course, it is not dissolving in air, but it is nonetheless getting evaporated, and there is a reduction in diameter. So, the phenomena basically is identical. So, therefore, it is possible to calculate the initial rate of dissolution only by substituting Km is equal to half. But if you took Km to be a function of d to the power half, in that case what happens is you have to integrate this, because this side is going to be a function of r. So, how you are going to do it? So, we will say that, look, in this case, if you take this particular reaction, then we will say that Km is equal to beta into r to the power minus half. That is the equation that will come from this variation. Schmidt number is constant, Reynolds number, all parameter is constant except the diameter, and then the diffusion coefficient is constant here, and from here if you manipulate, then we get this where beta is a constant, which is a function of, when b into beta, Schmidt number, then the kinematic viscosity, the diffusion coefficient, the factor of 0.6, all are engulfed in this constant parameter. So, therefore, under that condition you can have that minus dr dt, and then we have Cs star by rho s, and then we have mass transfer coefficient, and that is going to be beta raised to the power r to the power minus half, okay, as I have indicated. So, there beta raised to the power half. So, we can integrate this now, and this will exhibit then we integrate within the limits that I have already indicated. So, now the profile is going to be coming like this, because you have taken the exact variation of the dependence of Reynolds number on the diameter and mass transfer coefficient on the diameter. You have acknowledged by considering mass transfer coefficient to be proportional to r to the power minus half, and as a result of which you are going to get some deviation from the linearity. So, the complete melting time, this allows you to predict, for example, a priori that if you increase the stirring condition, what will be the effect on dissolution. Okay, that will be exhibited in terms of the mass transfer coefficient parameter as it is indicated. This embodies the stirring, the intensity of stirring, what stirring you should be applying. Okay, and then what should be the concentration, the complete melting time, what should be the size, because if you add a bigger size, in that case it will take for example longer time to dissolve. then and you have a finite processing time. For example, when you make alloy steel, you kept everything in a container, okay, in a vessel. For example, this is a ladle into which molten metal is kept, and in this molten metal you are adding, and the dissolution is going to take some amount of time. So you have a fixed amount of time available at your hand in the industry, and you want that you should be adding, such a size of the particle which will completely dissolve. Of course, the particle dissolves and then the particle mixes in the system. We want a homogeneous alloy. That is a different issue altogether. We are addressing here dissolution and not the mixing. That is a subsequent problem, of convection diffusion, combined convection diffusion phenomena. That is different, that we are not talking here. So we want to know that whether we would add this bigger diameter or this smaller diameter, so that within the stipulated or the available time, whether the alloying additions is going to melt. And we know that if you add bigger particle, then we can have to have good amount of stirring. But if you have good amount of stirring, then what happens is there is interaction between molten metal and ambient atmosphere increases. Also interaction between refractory wall and molten metal increases, and these will tend to contaminate the molten steel. So a priori simple design calculations can be performed in order to tell one that what is the optimum level of stirring, what is the optimum size of the particle that can be added, within the given jurisdiction of the time, such that one can result complete dissolution. You must understand, I would just like to mention that the complete dissolution time of alloying additions is typically much longer than the mixing rates, because in the bulk of the liquid there is going to be enormous amount of turbulence present in the system. So if for a given size, typically we would be adding this size lump, so which is about, I would say, a 25 millimeter radius. There's a 5 centimeter diameter or so, that is the maximum size of the particles. And when you add those solid particles, depending on the alloying additions, whether it is tungsten or niobium, etc., they can take something like 600 seconds, 700 seconds, which is like about 10 minutes to dissolve into the bath under a moderate amount of stirring. But if you compare that after dissolution, how much time will they take to homogenize into the bath, then you will find they are possibly only 50 seconds or 100 seconds of that. So by the time the dissolution is complete, actually the bulk remains well mixed, and in most of the metallurgical systems, because there is stirring always present, the subsequent mixing following dissolution is not a matter of concern. So it is the dissolution that needs to be properly engineered in terms of stirring, as well as the size ranges that one would like to add to make the alloying additions practical. We'll move on to the next problem now, which is again a solid liquid mass transfer problem. And this is unlike the dissolution process, but nonetheless we will encounter various processes that we have studied. So reduction of iron ore, so we take hematite, by CO. Yes. So this is the problem. Let me pose the problem. This is of enormous practical significance, because if you want to understand, the reduction of iron ore in the blast furnace, this reaction kinetics, the mechanisms that how the reaction is actually proceeding, that needs to be studied. And also the rate at which iron oxide is getting reduced in the blast furnace is very important, because that rate of iron oxide reduction will determine the rate of productivity. And every steel plant tries to produce more and more, because more you produce, more money you make. So that is good for business, it's a good business proposition, but that requires understanding of the intricacies of gas. This is a solid and this is the gas, so it is again a gas solid reaction. So this is like mass transfer between a gas and a solid. Now how is the process taking place? So we will consider only one step of the reaction, although we know that the reaction goes in something like this: Fe2O3, then Fe3O4, then FeO, and then Fe. That's the way. We will not consider all these steps, but we will consider that only the reduction is taking place, and we will illustrate with respect to this, because otherwise it will get the same philosophy that I am going to discuss here can be extended, if you consider from here to here. So you start with a spherical lump of hematite ore, and at some point of time, so this is being subjected to carbon monoxide gas at a suitable temperature, could be about 900 degrees or 800, 600, 700 degrees centigrade, and as a result of which this reduction reaction is taking place. Fe2O3 solid plus CO gas is equal to Fe2 3O4. This is 2, this is 3, and this is solid, and this is CO2 is produced. At some point of time, so this is initially Fe2O3. As the reaction proceeds, you will have something like a product layer formation, and this product layer formation is basically your Fe3O4. And this is now, so this is not at T is equal to 0, not at T is equal to 0. After some time, the reaction has started, and then this is the scenario. And this interface is moving as a function of time. Okay? So this is akin to a pseudo steady state problem, as you all know. Everything else remains, after some time, everything becomes steady, but this boundary continuously gets on. And also we see from this, it's a case of equimolar countercurrent diffusion. Carbon monoxide goes inside, carbon dioxide comes outside. One characteristics of this product is because there is a volume change typically when such reactions takes place. So we will have, there are going to be cracks in the system through which the carbon monoxide will go. And also there is a bulk material through which also carbon monoxide will go inside, because carbon monoxide will now show that there is another layer here, the yellow colored layer, and this is my gas boundary layer. Because it is solid, at the surface of the solid the velocity is going to be 0. So as a result of which we can say that there is going to be a boundary layer, and outside the boundary layer is the bulk. And the concentration of C0 carbon concentration is the bulk concentration. Now, if you look at this, so this is the, I will say, boundary layer, and then we have, this is the gas solid interface, and this is the Fe3, Fe4, O4, Fe2O3 interface, and which is the site of the reaction. So the gas from here comes to the edge of the boundary layer. So bulk transport is assumed to be first. Now, first step is that it crosses the boundary layer, it reaches this solid gas solid interface. Okay? So I would say this solid is, to be specific, Fe3O4. That is the solid, because there are two different solids, so let me isolate it. So diffusion, transport, not diffusion, transport through the boundary layer, and then diffusion through the solid, diffusion of gas through the solid. And as I said, because of the density change, there are cracks in the system. So carbon monoxide will pass through these cracks and try to reach this interface where the reaction is going to take place. Alternatively, carbon monoxide from here can transport through the bulk also. So there is a parallel transport, and this we have studied, okay? And I have said that we can, in the context of grain boundary as well as the lattice diffusion. So therefore that concept can be applied, and here the diffusion could be represented by an effective diffusion coefficient. Okay? So, the volume average values of porosity versus the bulk, that can be taken into account. So, the area average diffusion coefficient can be treated, and so we therefore should be able to, but it is not just D, it is D effective, and that D effective is going to be the diffusion area average diffusion coefficient with respect to the pores vis-a-vis the dense material. And then once the transport takes place, then carbon monoxide sees Fe2O3, the reaction thermodynamically, the reaction can travel in the forward direction, the favorable condition has been created, and we want the reaction proceeds from left to right. Now, as the reaction proceeds, so there are 3 steps right now I have said: transport across the boundary layer, diffusion through the solid layer, and then the chemical reaction. As the chemical reaction takes place, we have carbon dioxide which is generated. So, the carbon dioxide comes out or diffuses in the opposite direction to carbon dioxide, in this direction, diffuses through the solid Fe3O4, and then carbon dioxide reaches here, and then carbon dioxide transports across the boundary layer, and then the carbon dioxide is distributed in the bulk. So, there are 5 steps, 2 steps with respect to the reactant reaching the interface. One is the chemical reaction, and the other 2 are the mass transfer step associated with carbon dioxide, the product gas itself. So, we will not consider first the product part, we will consider that, look, we are not assuming that the reaction is at equilibrium. So, there is a finite rate of transport here, there is a finite rate of transport here, and there is a finite rate of reaction here. These steps, the 3 steps that I have said, these 3 steps work in series. So, their resistances determine the overall transport of carbon monoxide from here to here, okay, to the reaction interface. So, it is not only earlier what we said in the context of your dissolution problem, I said that it is only the boundary layer mass transfer which is rate limiting, the transport in the bulk as well as the interfacial reaction are at equilibrium, but that assumption I am not going to make here. Okay? The diffusion is slow, so is the reaction which is slow, so is the boundary layer transport. So, these 3 steps together working will only produce a carbon dioxide or produced, which is the product phase itself, Fe3O4. So, therefore, the rate at which carbon monoxide is transporting across the boundary layer, okay, and this carbon dioxide, whatever carbon dioxide reaches, that carbon dioxide moves through the via diffusion across the solid layer, it reaches here, and that much carbon monoxide is only available which in accordance to this particular reaction causes carbon dioxide to produce and at the same time reduce Fe2O3 into Fe3O4. Now, as far as boundary layer mass transfer, for the first step, rate of the first step, and the overall rate, therefore, I will say overall rate is rate of process 1, rate of process 2, and rate of process 3. Where first step is the boundary layer transport, second is the diffusion through the solid, and third is the chemical reaction, and this is the overall rate of, because they are all working in series. None of the steps, and there are altogether 5 steps, but the product part I am not considering because that will unnecessarily make the discussion lengthy. I do not have much time, so this will illustrate the principle, and you can also accommodate that if I add R4 and R5. Now, R1, for example, is known to us. The rate of transport across the boundary layer n dot CO is equal to 4 pi R0 square, this is surface area, into the mass transfer coefficient, okay, and then we have what is the concentration difference? The concentration difference here is the bulk concentration, and let us say this concentration is the surface concentration. I do not know that surface concentration. I know the bulk concentration, CCO bulk minus CCO surface, and that surface is this particular surface. This is, okay, I will circle it so that you can understand. This is the surface, and that is, and where the concentration is CCO surface. That is the driving force for boundary layer transport. So the gas has now reached there. Now in spherical coordinate system, if you remember, I have already derived the flux equations as well as the transport equations. Okay? And for spherical coordinate system, let us look at here. If you remember that the flux expression I write here as n dot CO. So if I write n dot, and that n dot CO is going to be 4 pi Ri square. So R square, it has reached here. So I will say R square, I will write at any R, and then this is D effective, that is the diffusion coefficient, and dCCO over. We know in the spherical coordinate the flux is proportional to R square. So this represents the net rate of transport at any R value, and this is applicable within where R is greater than equal to R out and R is greater than is equal to R in. What is that R in? And this is, I will say, this radius essentially gives me the RO, and this is Ri. RO is a fixed parameter, but Ri will be changing as a function of time because it is a pseudo steady state diffusion. And as I said, that at any point of time, when I know this, I can, if I know the Ri value, I should be able to find out or do the calculation itself. So if you represent it in integral form, okay, if you integrate between here and here, so what is, we know that at R is equal to R0, I have already said that concentration of carbon monoxide is equal to CCO surface. That is the surface concentration here at Ri, at R0. What is the concentration here? The concentration here is, I will say, is C0 interface, and that interface essentially means it is the reaction interface here. Okay? So therefore, R is equal to Ri. Note that, as I said, I will not write it as a Ri within bracket as capital, small t, that is a function of t, but you must understand that Ri is not constant, R0 is constant, and this is C sub C0 is equal to C sub C0 over I. So I should be able to, and this parameter, we know that if you take any R values, this should be constant. N dot CO, because I have multiplied it with 4 pi R square, this represents. So I have to put the value of R, and it is at that particular R. So whatever is the value, that is going to be N dot C is the net rate of transport. It is not the flux, it is kg mole, say for example, per second. And we know because it is multiplied with area, okay, that is why we would expect, while the flux is proportional to R square. And what is the shell balance equation? If you remember, the shell balance equation for this particular case is R square Na is equal to constant. So the flux is proportional to 1 by R square. Now in this particular case, this is not the flux, so this is constant whether you take here, whether you take here, whether you take here, and therefore one should be able to integrate this expression. And how do you integrate this? We can say that that is the way one should be able to integrate 4 pi d effective by n dot CO and dCCO, and so I will integrate this between the limit R0 to Ri and corresponding concentrations as I have seen. So R0 is C0 surface and CCO surface and CCO interface. Okay, if you integrate this term, okay, if we have already derived, so we can say that n dot CO comes out to be 4 pi d effective R0 Ri. This is derived in the context of when I have shown Nusselt's number is, Sherwood's number is equal to 2. This is the exact equation that I have derived earlier, and in this case, the flux is going to be related. This is rate of transport, that is going to be related, whatever flux from the flux expression, that flux is from the outside to the inside. So earlier problem we have only considered that the center is at r is equal to 0 and the flux is outwardly directed. Now the flux is in the reverse direction as far as carbon monoxide is concerned, but that, in terms of the governing equation, in terms of the boundary conditions, that produces no problem at all. And this is R0 minus Ri into, we will say, now the concentration difference comes C surface concentration, so CCO surface minus CCO interface. So this is the first step, rate of transport of carbon monoxide through the boundary layer. This is the second step, rate of, or I would say this is 1 and this is 2. And now we have to find out that what is the value of R3, how you can represent. And once we have found out, that is what I am going to discuss in the next class, that n dot CO. So this is from the reaction. Now by considering that the reaction is not at equilibrium, there is a finite rate of the reaction, there is a forward rate, there is a backward rate, there is a net rate, and based on that I should be able to also find out that what is the net rate of transport. And we must understand that because it's a steady state problem, so whatever net rate of carbon monoxide reaches here, that is the rate of carbon monoxide, because this interface cannot accumulate carbon monoxide gases here, otherwise the process will not occur and it is not possible also. So therefore, whatever carbon monoxide at steady state condition, because it's a pseudo steady state problem, whatever CO reaches here, there is the same rho which reaches here, and then the same CO actually gets consumed in the reaction process. But by considering the forward and the backward reaction which is taking place, now what is the driving force here? Because the reaction is taking place and there is, as I said, there is an interfacial concentration. But this reaction, where it is trying to go? It is trying to reach the equilibrium. Okay? So the driving force, an expression can be derived here, just like the way the driving force of diffusion is this, the driving force for boundary layer transport is this. We can also formulate the term in terms of interface, that it wants to go to equilibrium. So this represents the driving force. I will show that, which I am not, I do not have enough time for today's lecture. So this is the driving force for chemical reaction, and that we will see. So the third term we will be able to find out, and then we will see that all these terms are actually should be equal, because of the simple fact that there is no scope for any accumulation. So therefore, by summing them up, the overall rate of the reactions can be found out. We will continue with the discussion.